In this lesson from chapter 10.7, we're going to talk about several problems that involved inscribed and circumscribed polygons. In this problem, we have a circle that's inscribed in a right triangle, and also another circle that's circumscribed about the right triangle. We know that AB is equal to 5, BC is equal to 12, and that AB is perpendicular to BC. We also know that because circle D is inscribed in the right triangle, we know that there are several tangents that connect with circle D, and those tangents are AC, BC, and AB. So if we know that AB is 5, we're going to say that first we'll call this point F. We know that BF we'll call X, and then we'll know that AF is going to be 5 minus X. If AF is 5 minus X, by the two-tangent theorem we know that AE is also 5 minus X. Additionally, we know that BC is 12, and we know that we'll call this point G. BG, by the two-tangent theorem, is also going to be X. So GC is going to be 12 minus X, and EC also is going to be 12 minus X. Well, we know that AC is going to be 13 units because we have a side of a right triangle is 5, another side is 12, so we have our special triple in this particular right triangle, a 5, 12, 13 triangle. So if AC is 13, then I know that 5 minus X plus 12 minus X is equal to 13. Or I can say 17 minus 2X is equal to 13, or minus 2X is equal to negative 4, or X is equal to 2. If X is equal to 2, then AF is equal to 3. AE is equal to 3. And EC is equal to 10. So in this particular case, we want to find the ratio of the areas of the smaller triangle to the larger triangle. I'm going to move on to a different page. In the smaller triangle, we know the radius is going to be 2, right, because that's going to be X. And in the larger triangle, we know that this is the diameter because an inscribed angle in a circle that's a right angle cuts out an arc length of 180 degrees. And that arc AC is your 180 degree arc length. And AC, the segment, is also the diameter. So if AC is 13, I know the diameter, or the radius, AE, is going to be 6.5. So the area of circle E is equal to pi times the radius squared, which is 6.5 squared. And the area of circle D is going to be pi times the radius squared. Well, 6.5 squared is 42.25. times pi to 4 pi. Now when we're talking about relationships or ratios, we want to make sure that all the values are whole numbers. So in this case, we're going to multiply both sides by 4 so that both of them are whole numbers. And we get 169 to 4. Now the pi's don't matter in a proportion because they reduce each other in the proportion to 1. So we don't state them here. And this is your answer. In the second problem, we have circle P that's inscribed in trapezoid WXYZ. We know the radius of circle P is 5. And now we're trying to find the perimeter of WXYZ. Well, we know if the radius is 5, we can again draw a square. So I know that the radius to the tangent forms a right angle. I know that WZ and WX are perpendicular, and WX and XY are perpendicular as shown. So I have two squares, one at the top and one at the bottom. So I've got half, or roughly half, of the problem figured out. Now I have to figure out the second part. I'm given that YZ is equal to 14, but how do I find the remaining distances from this point of tangency to Z, this point of tangency to Z, and this point of tangency to Z, or I'm sorry, this point of tangency to Y? Well, let's start by identifying those lengths as variables. So I'm going to say that this point here is going to be A, and this point here is going to be B. So I'm going to say that from A to Z is going to be C units. And I know again by the two-tangent theorem that this length here, we'll call it E to Z, is also going to be C units. So from E to Z and A to Z, they're both C units long. Then from B to Y, I'm going to call that distance F. And then again, E to Y is going to be F. So based on what we're given, if YZ is equal to 14, then I know that F plus C is also equal to 14. Well, it just so happens that AZ plus BY is also F plus C. So now I've figured out my unknown lengths. So now I can add YZ, which is 14, plus AZ and BY, which is also 14, plus the value of these distances here from WA, W to A, W to X, and X to B, and those all equal 20. So my perimeter ends up being 48 units. In the last problem, we have a circle inscribed in a triangle. We know that AB is equal to 8, AC is equal to 12, and BC is equal to 10. Now it's not stated that this is a right triangle, and in fact if you work it out, it is not. It ends up not being a right triangle. And what we're trying to find is what X and Y are, and what their relationship is in terms of a ratio. Well, I'm given that AB is equal to 8. So I know that X plus Y is equal to 8. Here we're confronted with another walk-around problem. And so what I'm going to do is, and also a problem involving the two-tangent theorem, I'm going to say that this length here is X. Let's call this point D, and let's call this point E. So BD is X, DC must be 10 minus x. And I know that a, we'll call this f, or y, is equal to ae. So I'll call this y. And I will call this also 10 minus x, because by the two-tangent theorem I know EC, again, is equal to DC. So now I have another equation, and that equation is y plus 10 minus x is equal to 12. And from my prior equation, I know that y is equal to 8 minus x. So now I'm going to use substitution to solve the value for x. If I have y plus 10 minus x, I can take the value of y, which is 8 minus x, and then substitute it in for y and solve for x. So I have 8 minus x plus 10 minus x is equal to 12. So 8 minus x plus 10 minus x is equal to 12. Or 18 minus 2x is equal to 12. Or minus 2x is equal to negative 6. Or x finally is equal to 3. So now I have the value of x, which is 3. I can find out that y is going to be 8 minus x, so y is going to be 5. So the relationship of x to y is going to be 3 to 5, or 3 over 5.